very basic introduction. Actually, the most basic introduction you can get in science. I don't know if this introduction was ever given to you, and this is about the scientific, I call it the scientific wheel, the wheel of science. How do we do science, and where in this paradigm probability and statistics come in? And the reason I give it is because, especially in physics, this is the physics class. In first year, students think, okay, they learned mechanics and then they learned electrodynamics, classical mechanics and electrodynamics, and then they come to think that, okay, there are equations for everything. The equations are exact. And if I am given a problem with some initial conditions, then there is a solution, and the solution is exact, right? So you have, let's say, I'm giving you a problem. You have point mass here at the height of 1 meter, and the gravity, acceleration gravity here is g, and I really can ask myself, what would be the falling time? Okay, and what would be the speed? This is something you can easily answer. And you come to think that the answer is exact. But then you come to a lab. You have been doing lab work, yes, right? And you're said, look, yeah, there are the laws of physics, but whenever you take measurements, let's say of a time, so my measured time is something that your clock told you. So I don't know, let's call it t. So this is a number you have measured, but then they tell you the instructors, but please put here plus minus sign and then some delta t. Okay. And usually nobody takes their time to explain you what this is. Right? And reality is that when we write such a thing, what we usually have in mind is that on the scale of time from 0 to infinity, the time of the event, so there was an event in nature, let's say the falling time of this point mass. I always say point mass, although it's not really point mass, but this is how you solve problems until you get to learn about rotation and so on. So there is some, okay, maybe let's call it t prime. So it's a number. This is the variable. So there is some number that you have measured, but you are not certain to 100% that the actual value in nature was this number. Instead, you have some uncertainty. You have some measurement uncertainty. So this is the uncertainty. And even more precisely, what people have in mind is that the probability distribution function, and this is what I'm going to write here, PDF, is probability, or if you wish, density function, has a shape of a Gaussian, which is a given function. The function is an analytic function. It looks like this. The center, the peak of the function is at t prime, but it has a specific shape, which we will learn, I think, 3 weeks from now. And the width, or half of the width, is delta t prime. So the purpose of the next 3 weeks or 7 meetings would be to give you the tools to understand what is probability density functions, how they are calculated, and how they are used in order to later solve the statistical analysis problem, which Yossi will give you. For example, if you have some x and y, doesn't matter what these x and y are. For example, it can be now another problem of a parabolic not short trajectory. Yes. So let's say you have thrown, and again you have some initial conditions, right? Now let's imagine you're taking a video. Actually, we are now taking a video. And from this video, later you extract the position of this point, the positions of this point mass along the trajectory. So you have some starting point, let's call it here at 0. You have some ending points, x end, and you have some points along the trajectory which you extract from the video. But again, you have the measured positions, but within some uncertainty, because in reality, all measurement instrumentations are not 100% accurate, right? They have what some people call error. Okay, and then after taking these measurements, so these are the measurements. Sir Isaac Newton comes to you, tells you, look, I have a model for this trajectory. And the model is parabola, and it has a shape like this, and it has some parameters. So my model is y of x equals some a0, some offset, plus a1 x plus a2 x squared. Now these are model parameters. The functional shape of my model, of the real trajectory in nature, not the measured one, not the one that you have recorded, but the real one, right, is dictated by the laws of physics. And there is a reason you can develop, I mean, you can express these parameters with some physical parameters of the problem, which is actually, I think, was given to you in Mechanics 101. But in the specific problem of your experiment, of this probe, okay, sometimes you don't know the parameters a priori, but you want to extract them from the measurement. And you do so by fitting. So this is a fit. By fitting, by tuning the parameters, okay, to best fit the model to your measurements. And in this process, this is called linear regression, and Yossi will or have already taught you how to do this. And in this process, these probability density functions are used and heavily used, and we will learn exactly why Gaussian and how independence, for example, one of the assumptions in the linear regression, best fits Nazareth by linear regression. And for example, the normal linear regression procedure that Yossi have taught you and you will implement there is an assumption, a hidden assumption that all the measurements are independent. All these measurements are called IID sets. This is in IID is independent and identically, that's the second I, distributed. So all the measurements are independent and identically distributed. For now, it doesn't tell you anything, but in the next 3 weeks, we'll learn what does it mean mathematically to be independent variables and what distribution means. Okay, density and distribution are equivalent words. And what does it mean that they are all identically distributed? Okay, and this assumption will be used in the development of the linear regression procedure. Okay, so we kind of, because of the constraints, we kind of inverted the order. So we started with statistics. Usually we learn it the other way around. We start with probability, and then we go to statistics. In this semester, we started with statistics. So you get the tools that basically the implementation, which statistics is the implementation of probability to the problems of usually experimental physics. So the wheel of science goes like this. We have nature. We have the physical nature. And in the physical nature, we have all kinds of phenomena. And you can think of any phenomena you want, an atom or a stellar system. For me, it's easy because I also teach astronomy. It's easy to think of the history of astronomy. Let's think of a planetary motion. And this is the problem that Kepler and Newton had in mind in the 17th century. They tried to understand why planets in the solar system move as they move around the sun. That was already after Galileo Galilei. It was already well accepted that planets move around the sun and not vice versa. Kepler noticed that they move in ellipses and not in ideal circles. That was 1609, more or less in parallel with Galileo Galilei telescope observations. And what Newton did in his book Principia, he actually he proved why planets have to move in ellipses from first principles. And the first principles were the laws of motion of Newton. So the 3 laws of dynamics and the force of gravitation, the universal gravitational law of Newton. So these 4 equations basically, with some additional algebra, in the problem of 2 masses, you are given m1 and m2 with some distance between them, r, and some initial conditions of v2 vector and let's say v1 vector. So this you have here 6, 7, 8, 9 numbers, right? You have, this is a 3-dimensional vector. This is a 3-dimensional vector. This is 2 scalars, and basically R0 is the initial distance between. This is sufficient. So these 9 numbers define exactly the trajectory of these 2 masses in space. I should say in the coordinates, in the center of mass coordinates. So let's, if there were equal mass, the center of mass would be here, but let's say m1 is the sun, so it's much more massive. So let's say that the center of mass is here. So in the coordinate frame where the origin is at the center of mass, they will move indefinitely till the end of times in a given two ellipses. So M1 will be doing a small ellipse here, and at the same time M2 will be doing a big ellipse there around M1, around the center of mass. Actually, this is what happens to every planet actually, every pair, planet and sun. Now, what Isaac Newton wanted to do is, or did actually, is to show the empirical law of Kepler about ellipses. So Kepler only stated it as a fact. The fact is that it's an observational fact. Planets move in ellipses around the sun. More accurately around the center of mass, but it's very close to the sun. So yeah, it's for their precision, it was indistinguishable. What Newton did is developing a physical analytic model from first principles. He stated the principles, and now he has a model for this system. Now, when I say wheel of science, I mean a wheel, so science or physics only starts here. Once we have a model, what we do, or what the model gives us, let's work in this direction. The model models give us predictions. Okay. So this is, in this region, you'll have theoretical physics. Physics. For example, this model gives you not only the points where it should have been, your point mass, in times where you have measured it, but also all the points in between. It's a prediction. It tells you if you would have measured here, this would have been your result. This is called interpolation. Yes. It also gives you an extrapolation. If it will continue falling, so half a second later, if you make a measurement, the position will be here. Okay? So a physical model gives you a prediction. Okay? So whenever you solve, let's say, your home assignment in electrodynamics now, and next course in quantum mechanics, whatever you calculate is a prediction. It's not a reality. Okay. So to verify, to make sure that reality actually behaves like the theoretical model, what do we need to do? To check whether reality actually behaves like the theoretical model. Чтобы проверить, если реальность по-настоящему работает как наша теоретическая модель. Что мы делаем?
We have to check it experimentally.
Exactly, we have to do an experiment. So next thing we do in the wheel of science, we design an experiment. Okay, so we devise clocks and rulers and say, okay, we write, okay, we'll start dropping things from this height and from this height and check whether G is constant and so on and so forth. So we design an experiment. After designing an experiment, we have to build or devise the instrumentation. So instrument construction. And eventually, we do the experiment. Okay, so this region of the wheel of science is ruled by instrumentalists. So here we have for instrumentation. So in this region, we have the theoretical physicists. Here we have usually engineers, people who design and build instruments. And of course, here we have experimentalists. Who actually do measurements, take measurements. In my field of research, for example, in astronomy, experiment is actually an observation. We take a telescope, we observe, and we check whether the stars really behave like we think they should behave. After completing the experiment, what the experiment provides, what you are left with after doing an experiment.
After experiments, we have data.
Data, exactly. You have taken notes in a notebook or maybe on the computer. Maybe you have images, maybe you have tables. Nowadays, everything is tables, even images are tables, if you think of it. These are big matrices of numbers, right? Every image is eventually a big matrix of numbers. Okay, because everything is digital now. So the experimentalists provide us with data. But this is not enough, because to close the loop between theory and experiment, we need another tool. And this tool is what in philosophy is called a truth maker. We need a truth maker to check whether the theory is true or not. And the truth maker, believe it or not, is statistical analysis. Or if you wish, more generally, data science. Now, what data scientists provide here, and this is not this is a philosophical concept, but a very important one. It provides like a flipping coin. It provides a confirmation of the theory or a refutation of thereof. So there will be a statistical test. So this is done by statistical tests. And we'll learn, maybe you have shown already the chi-square test?
Yeah.
Okay, with its p-value?
Yeah.
Okay, perfect. So the chi-square test is the first test you learn. There are a few others, more complex, but the first test to tell you whether this model, given the data, is adequate or not. Okay? And this closes the loop. Because if the p-value, let's say if the p-value was too small, for example, the statistical test will give you always some kind of a p-value. Now, a p-value, it's called a p-value because it's a probability. Probability. It's not just probability. Usually, it's the probability of the model given the data. So it's kind of a conditional probability. This also doesn't tell you a thing for now, but it will soon. What does it mean? Probability, we'll learn today. Next week, I'll explain what is a conditional probability. Conditional probability is a probability of something given something else. So let's say of event A given an event B. And ask yourself, for example, in a family, given that the first child is a girl, what's the probability that the second child is also a girl? That's a conditional probability. Okay? if I have COVID, what's the probability that on the 9th day of my COVID disease, I'll still have symptoms, which is the case for tomorrow. This is a condition for, okay? Okay. So this is what we do in physics. This is what we do in general in science. And this is why this course is so important, because I will not be teaching any physical models. We will not be doing any experiments, but we will be learning how to treat data. Okay, how to treat data. So we'll be working in this area, and how to close the loop between experimental physics and theoretical physics. Okay. Questions thus far?
No, I'm writing. Okay. Even I think that I understood what is conditional probability.
Probability.
But okay.
Ask whatever you want.
Yeah, and the confirmation or refutation, it's like proving or disproving.
Exactly. What I'll show up in reality, honestly speaking, we cannot confirm anything with statistics. We can only refute. But the general convention is that if we can prove that the model is wrong. We cannot prove with real data. We cannot prove that it is correct, but we can prove that it is wrong. The general convention is that if we fail to prove that it is wrong, then it is an adequate model. Okay, this is the curse of statistics. That the only thing we can do is to fail proving that it is wrong. That's the best thing we can do for theoreticians, is to fail disproving their model. If we fail disproving their model, then their model is adequate. This is what the experimental physicists do for example, for a whole century. People search for experiments to disprove the theory of relativity, Einstein theory of relativity, or the quantum mechanics. As long as this theory withstands all the tests from 1916 till now, it's a good theory. If, for example, 5 years from now, we will have an experiment that will be inconsistent with general relativity, then we will say, okay, this experiment had refuted general relativity, and the model is no longer adequate. We need a different model. Okay. This is something that actually happened to Newtonian mechanics 100 years ago. So Einstein had shown that in some extreme scenario, like of either extreme speeds, like with special relativity, or extreme gravity for general relativity, laws of Newton fail in predicting reality. So he devised a new model which is more adequate. Okay. So this was the introduction to science, and why we need probability and statistics, why it's so important in science. And now let's talk a little bit about probability. So I will be teaching, as I wrote in my email, I will be teaching from the English book. And since we have 7 meetings, including this one, we have 7 meetings plus last one, or if anything's left. I will be going at the pace of 2 chapters per week. So in the last and 7th meeting on, I think, September 4, we'll reach to chapter number 14. in the book of Modern Introduction to Probability and Statistics, which deals with the central limit theorem. So the central limit theorem is the topic that connects probability with statistics. Let me give a very brief introduction to the concept. So I will start I will start with the main concepts of probability, mainly definitions. And not today, but next week we'll go on to combinatorics and actually making some calculations. Although even this week, in every class, every meeting, every day, I will give a brief home assignment. It will be from the book. Okay, so I'll just give the numbers of the home assignment. For some of the home assignments, for some of the home questions, you have at the end of the book full solution. For some of them, you have only a partial solution and the end solution, and you'll have to develop the full solution yourself. Okay, so probability. Basically, I'm talking about definitions. Probability, simply speaking, is a real number from the range of 0 to 1, inclusive. Okay? Any real number, so probability, when you are asked what is the probability of, the answer should be a real number between 0 and 1. That is probability. Okay. Now, it's not saying anything, but intuitively, what it gives us is an estimate, a numerical estimate, okay, of the likelihood of an event. Okay, where 1 is total certainty that the event will happen for sure. 0 is total impossibility, that there's no chance that the event will happen. And anything in between gives you the likelihood that the given event, the event at hand, will happen. So basically, it's a function. So probability, let me write it in the appropriate mathematical terminology. I have it in my Hebrew.
May I add that likelihood is a number that you have measured. Okay, it's not probability, it's likelihood, it's the number of the actual event that you measure. It is sometimes problematic to understand. Yes, what means difference? What is the difference? Something is theoretical and something is practical. Likelihood is the number that you got from reality.
Yes, it's the difference between theory and experiment. So probability is like the theoretical prediction. So I don't have it here, but okay. It's a function let's call it the event space to real space. Real space, you know what it is, right? It's the one-dimensional space of real numbers. Okay?
Yes.
Event space, you don't know what it is, and it's actually it's a concept. It's an abstract concept. It's an abstract space of events. So the let's say the fact that the prediction that the sun will rise tomorrow is an event. Okay, but it has no numerical representation. Okay, it's an event. It's taken from the event space. If no, I don't have a point. Do you have a point? I'm out of points.
And maybe so they are probably all
So if I toss a coin, okay. Okay, I have a coin with two sides and I toss it. Okay, okay, I'll toss it here. I toss it and I look at what is the upper side. This is an event. It has no numerical representation.
It's something like categorical or discrete.
I can translate the event to, let's say, possible outcomes. Okay, the event can have possible outcomes. Or if you wish, the experiment. Actually, the single events are the possible outcomes. The different possible outcomes of a physical experiment are called events. So this is the experiment, physical experiment. It has two possible outcomes, let's say head and tail. This is how they are called in English. And a probability function gives you a prediction, a numerical prediction. It translates each event, it assigns to each event a number between 0 and 1. Okay.
So
This is important.
likelihood? No, probability
Mhm.
is theoretical. So theoretical is always 50-50.
No, doesn't have to be.
I
It's something between 0 and 1.
would like to say that likelihood that we will do it maybe 60 and 40, not always 50.
Mhm.
So
So, for example, for a fair coin, a fair coin is unloaded coin. The prediction would be 50-50. So each event would have, you have two events. Let's call them, okay, let's take this example. Tossing. We'll use this example many times, so it's a good place to tossing a coin. So it has an event space. The event space usually placed in brackets like that, in which I write inside all the possible outcomes, all the possible events that can be outcome of the experiment. Single toss of a coin has only two possible outcomes. I'll call them up or head and tail. This is just names, okay? This is how they usually called. I prefer, as a physicist, I prefer to call them up and down. This is also because it's related to the spin of an electron. So you learn in quantum mechanics that there is some property of elementary particles, which is called spin.
yes.
And it has only two possible values, up or down. Given an external magnetic field, but let's put it aside.
Okay.
So the event space for this experiment, this is the experiment, it has an event space which has two events inside, up or down. the probability function assigns to each of these events a probability. So here comes a probability function, which, as I said, is a theoretical function. And if the coin is unloaded, meaning fair, so your prediction is that each of them has a probability of 50%. Each of these events. So here, in this example, we have demonstrated how the theory of probability works. You take a physical experiment. First, you map its event space. What are the possible outcomes? And then you use the theory of probability to predict the likelihood of each event in the space, in the event space. And these likelihoods are probabilities, so they are numbers between 0 and 1. Now, what is the motivation behind it? I mean, people have developed the theory of relativity along the 18th and 19th centuries mainly. It's matured towards the early 20th century. So the central limit theorem, which we will learn as the end point of probability, was proven in 1902, so more than 100 years ago. So the mathematics we'll learn in probability is the mathematics of mainly the 18th century. But what was the motivation? The motivation was actually an observational one. People have observed that given a large number of experiments, when you repeat the same experiment over and over again, let's say you toss this coin over and over again. So for example, you want to test this prediction. Again, this is a prediction. Your prediction, but unlike in analytic physics, right, where your prediction is a single number, in probabilistic physics, the prediction is probabilities. So it's a set of numbers, which gives you the probability of each event in this what we call actually random process. It's a physical process that has some randomness. So the motivation behind it is an observation which is called the convergence of the fractional occurrence. Words, even R. And I'll demonstrate it. Let's call this axis n. This n is number of coin tosses. And this is the fractional occurrence. Fn of let's say event C. Okay. So I'll put it here. No. See, let's use okay. H. Okay, head. So you ask yourself the following question. Yossi, can I have your phone again?
Yes.
I'm going to do an experiment. An actual physical quantum experiment. So let's call this this size, you know how it's looked at. So this size, let's call the tail, and this is the tail. Okay. So as I'm going to toss a coin over and over again, and on each step, I'm going to register whether this is a head or a tail, and the fractional occurrence will be the number of heads out of the total number of tosses. Let's say if I had 3 heads out of 10 tosses, the number will be 0.2. The fractional occurrence will be 0.2. This is the definition of fractional occurrence, right? For example, if a class has how many are you in this course registered? I don't know. I think we were 12.
What?
Students,
Ah.
I think, but so the fractional occurrence of students that actually came today to class is 1 out of 12. It's a number. It's a number between 0 and 1. So similar to probability, it's also a number of 0 and 1, but this is an actual physical real measurement. Fractional occurrence. Okay, so let's start. First thoughts, tail. Okay, maybe you yes, right for me.
Yes.
Tail, tail, tail. I think it's loaded. Tail,
Don't tell anyone.
tail. I have 5 tails in a row.
Really?
Head,
Wow, that's interesting.
head, head, tail, head, tail. Okay, let's stop here.
11.
So how many did we have?
Yeah, 11.
6, 7, 8, 9, 10, 11. Okay, so this is the number of heads, fractional occurrence of heads. It can be at most 100%. Okay. So we had tail, 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 right? Tail, 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 tail.
5 tails.
5 tails, and then
Head, head, head.
okay,
Tail, head, tail.
tail, head, tail. Fine. This was the actual real experiment. So how would the fractional occurrence look like? So it was 0, 0, 0, 0, 0 here until here, then 1 out of 6. So 1 out of 6, 2 out of 6. This is 1/3. 3, actually 3 out of 7. Then slightly down, slightly up, slightly down, something like that. So we reached to this point. The theory of or the observation of the convergence of the fractional occurrence predicts that if we will continue this experiment to a large number, we can do that, but I don't want to waste the whole class on you can do it at home. Eventually, if the coin is really unloaded, and I'm doing the experiment with no cheating, it will do like this, it will, but eventually it will slowly converge towards this prediction of 50-50. And this is an observational fact. Okay, and this is a fact that people noticed in the 17th or the 18th century, and they said, okay, so let's try to use this fact. It's also called the law of one of the laws of large numbers, that when you're repeating the experiment over and over again, at the end, your measured fractional occurrence converges towards your theoretically predicted probability. Okay, So this is the motivation. This was the motivation behind the development of the mathematics of probability. And then, in order to continue, we need some definitions, some basic concepts. So I'll leave the definition of probability. I'll erase the example and the motivation. The most important concept is random process. Actually, this course is called תהליכים אקראיים בפיזיקה, which is random processes in physics. So what's a random process? A random process is any physical process that can have more than one outcome. And I emphasize even when starting at exactly the same initial conditions. Now, again, I can give this example. And this is the difference between the classical physics that you have learned up until now and the real physics in the real world, or if you wish also the quantum mechanics and statistical mechanics, which you will learn next year. And this is the understanding that even real physical process, even if they start at exactly the same initial conditions, may end up with different results. In classical physics, we say, okay, if you start at this height, at exactly the same height, and you repeat this experiment over and over again, you should always get the same result.
With error, but still.
Okay, and here is exactly the difference. So even classical physics, the error is something inherent to reality. Okay? Because reality has some randomness in it. No matter how will I try to devise to exactly the same initial conditions, they will always be different. The air condition is slightly different. The Earth now moved a little bit. There is no such thing as exactly the same initial conditions. Moreover, there is what's called classical chaos. Tiny variations of the universe along this process cause eventually different results. Moreover, when you measure eventually what you have at hand as a physicist, as a theoretician, you have the prediction, but as an experimentalist, you have the measurement. The measurement, in addition to the error, it has measurement uncertainty. Because the measured, you only have the measured values. Your reality, if you think of it, your physical reality is made of measurements, is made of physical measurements. And any measurement apparatus, including our own natural ones, like our eyes and ears and sense of time, have inaccuracy, inherent inaccuracy to them. Even the most precise atomic clock is not infinitely precise. Even the most precise laser ruler is not infinitely precise. It has some error, some measurement uncertainty. So eventually, every physical process importantly, every physical process has some randomness in it. So randomness is unavoidable.
In it or in the measure?
In it, in it, in it. Because even if the physics itself was fully deterministic and analytic, even if it was like this, and even if your measurement apparatus would have been infinitely precise, which is not the case, even then, real physics is made of quantum processes and chaotic processes, which you will learn next year. So quantum, since every physical process at the bottom is a quantum process, because quantum mechanics describes the laws of nature at the atomic scale and subatomic scale, and everything is made of atoms. Every material is made of atoms. You learn that there is uncertainty. There is what's called the Heisenberg uncertainty principle. There is some inherent uncertainty in nature. So yes.
Yes, but when, okay. So, okay,
The
principle of uncertainty of,
Heisenberg uncertainty.
yeah. But when you come to macro situation, you say it's a Zolet. It must, because
Macro features, you can think of them as averages of many micro uncertainty. So I'm at the position where I am, and I'm not, tunneling through this wall, not because it's impossible, but because the probability is very small. Because my position is the average of all the positions of all the atoms I'm made of.
so the principle of Heisenberg is relevant also in the macro.
Yes.
Macro phenomena, macro.
Yes,
system.
but it's another law of large numbers, because when we go from micro to macro, we average out many small uncertainties to very, 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 very small uncertainty. But still, it's still inside. So eventually, every physical process is a random process. So at some point, I'll just stop saying random. And whenever I talk about a physical process, you should remember there is some uncertainty and some randomness in it inherent. So for example, when I'll talk about an experiment, so in principle, I should say a random experiment. This is what you will see in the book on probability, but I'll put it in parentheses, so I'll drop it all together because every experiment has some randomness in it. Okay, so experiment is the process of measuring the outcome of a physical process. So there are two things. Okay, there is, for example, the random process of dropping this thing, and there is another thing of measuring it. Okay, this is another process. Taking a measurement with the clock and the ruler and so on. And finally, important for probability is the sample space. Okay. Event space is also called sample space. So sample space is the collection of all possible, importantly possible outcomes of an experiment. Okay, like before, we had in our collection two possibilities, head or tail. If there was some probability that a coin will fall inside, then I will have to add that one too. Maybe that's
It has, but it's very,
very, very low. So maybe I should, okay, so it's 49.9999, 49.99, and 0.000 something percent to on the side. And so sample space is the collection of all possible outcome, a single possible outcome called an event, or a single or a subset. So event is a subset of one or more possible outcomes of an experiment. Again, I drop, when I say experiment, I drop the word random because every experiment is random. Now we can devise, and we will do so next week. We can devise all kinds of experiment and events. Now we can think of an experiment was tossing a coin once. We can also define an experiment like tossing the coin twice. Tossing the coin, not tossing the coin. Tossing the coin twice, and then, for example, how many outcomes are possible if I toss the coin? Four. So in tossing the coin, this is a different experiment. It's a new experiment, and this one will have like up, 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 down, down, up, down, down. So the event space now has 4 elements, and I can also define. So there are 4 simple events, but I can also define, because an event can be a subset, I can also define an event, like event A would be, I got the same result 2 times, and then these 2 would be my event. Or I got opposite results, and then it's these 2. Or I got up in my first toss, then it will be these 2, and so on and so forth. For every experiment, I can define many different events. And for each event, I can ask, what is the probability of that event? And this will be the topic of the calculations. Like, what is the probability of getting this event, or this event, or this event, or for example, I can define, let's say it's a pair of points, so I can define an event. The event is I got at least one up. So how many elements are in, how many simple events are in this event?
Three.
Three, and hence the probability of such event is,
One.
No.
Every-
I toss the coin, I toss the coin twice,
Yes.
and I ask you, what is the probability of the following event? I got at least one up.
This one up. We have three.
Yes. Out of? Out of how many?
Three, seven, four.
Okay. Can I have the coin? I toss the coin twice,
Yes.
and I ask you, what is the probability to get at least one up?
3 of 4, so 75%.
Exactly. Okay, that would be that. So, and this will be the topic of all the calculations we will do in your home assignment and also next week. I think it's a good place to start. Okay,
Let's say you want to have, let's say, 8 minutes break, and then we go straight 1 hour, it's okay? Good. Not, so there's something in that time. Yes. Continue at the 4:25.
so this is the book. And I should look here because otherwise I'll be everything very. So today we cover chapters 1 and 2. And chapter 1 is just introduction to probability. The way I gave it is a little different from the way the book gives it, because I give it in a physical context. And this is a general book of probability and statistics, so it does not necessarily speaks about physics. Although it gives examples from the measuring the speed of light, which is very physical, but never mind. Chapter 2 starts with the definitions of probability. So let's look at chapter 2 here, because otherwise I won't fancy.
Need a chair?
No, not really. So we have defined sample spaces. You don't need to write anything because you have everything. So the book is on Moodle. Download it.
Or you sent it in.
Maybe I didn't send it, I don't remember, but this book is on, this is what I call book 1. Okay. So we have defined sample spaces like heads and tails. You can stop a random person on the street and ask what is the, okay, Yossi, for example, what is your birth month? July. Okay, so here's the random, here's the sample space of his answer of this experiment. And maybe before Yossi gave his answer, you could assign one out of 12, or maybe each month, like February would have slightly lower probability, 28 out of 365, and so on. The probability for each outcome. And once we have a result, then all the probability of events is.
By the way, this is the formalization of a group.
Yes,
The theory.
yes. Probability uses mathematical tools of group theory. And there are a few other examples. Okay. So yeah, mathematical operations between let's say events or groups. This is all group theory mathematics. So the intersection of two events is when both events happen. Okay. For example, okay, here is some example. So the intersection is called is annotated. חיתוך, כן. So intersection is חיתוך. This is in Hebrew. It's very it's like
Intersection.
חיתוך.
Okay.
So-
So Hitok is intersection?
Yes.
Okay.
חיתוך is intersection when both events happen, and the union if it is if one of the events happen,
Mhm.
if at least one of the events happen. And this little c, A with C is the complementary event. This is not A, okay?
All of them except.
Yes,
Okay.
what is going on? Okay. This is the complementary event.
Sometimes it's easier to calculate the complement instead of the events themselves, and then subtract from one. So that's why it is important.
And a very useful tool in visualizing events in a sample space is called the Venn diagram. So the sample space, this is one way of depicting the Venn diagram. I prefer the square one. So let's say, right, your experiment is not tossing a coin now, but throwing a dice. Okay, a dice has 6 sides, usual shesh dice. So it has 1, 2, 3, 4, 5, 6. Right, this is the event space. This is the sample space. Sample space usually is denoted by omega. So this is omega. This field is omega. And you can, in this field, you can define events, right? You can, for example, define event A, which is, you got a number which is less or equal to 3. So this will be event A. Okay. You can define another event, let's say event, we'll call it event B, and event B is odd. So this is 1, 2, 3. This is 1, 3, 5, right? So we can call this B. Okay? So each of the events has 50% probability for a fair dice, right? This would be called, this field is A and B. So and is intersection. And in Boolean algebra is the operator and. So A and B happened. So you can see like and this is also an event, right? A and B, what it has?
1 and 3.
1 and 3. So what is the probability of A and B? For a
1
fair
and 3.
1 of 3. Okay. If this is A, then this is in the book's notion is A complementary. I prefer to write it A hat. This is not A.
Inverse.
Yes. This is not A. Okay, and this also not B. Okay. So, for example, this field is not A intersection, this little square is not A intersection with not B, right? But it is also the union of A and B. So A or B. So where should I write it? So this is a union, and it is similar to the Boolean algebra operator of OR. So A or B in this experiment, what it contains?
A 1, 2, 3, 5.
Exactly. 1, 2, 3, 5. So not A or B would contain
4 and 6.
4 and 6. So this is also not A or B. Okay. This whole G letter, it's either in Russian, because in Hebrew I have to say inverted yud. This G letter is A or B. This is not A or B, which is similar to not A and not B, which brings me to the Morgan rules. Okay, so not A or B is equals to not A and not B. Not A or B equals not A and not B.
Yes.
Okay, this is just nomenclature. And this brilliant idea is called the Morgan's law. Okay, very trivial logic for that. When you draw, but it's easy to visualize. I mean, this Venn diagram is a very useful tool to visualize the possible outcomes of events.
Yes.
Okay, later, for example, you have like more complex events. Like here, for example, let's say you have 1, 2, 3, 4, 5, a loaded dice. 1, 2, 3, 4, 5, but someone placed someone placed a load on the opposite side of 6. Usually the opposite to 6 you have 1, so someone placed there, so he will get more 6s. So the probability of 6 is larger. Okay, and on top of that, you have some another. So this will be A, and you have some another event B, which will be given that let's say maybe B will be, maybe you're tossing 2 dices, okay? Or maybe let's make it simple. You're tossing a dice A and the coin B. So B has only 2 sides. Okay. So and then these 2 events can be dependent or independent. So for example, for the independent, if the dice and the coin are not dependent on each other, so it will be flat, right? The probability of what you will get in the coin is not dependent on what you get in the dice. But let's say in some magic, they are related to each other. That the coin knows what happens in the dice, and if let's say if the dice is getting 6, it gets a higher probability. So there's a higher probability for, let's say, head with some magic.
Yeah.
Okay. So this is again an event space of 2 not independent events. So in such complex reality, again, the Venn diagram, I'm just drawing it because the Venn diagram is a very useful tool to visualize the probabilities of events. Okay, even in the exam, for example, you get an exam. So when I give a question of probability, and usually it will be some complex event. Let's say A can be some physical process, and B can be the measurement of that physical process. And sometimes the measurement is not independent of the process. Okay, let's say the process is, let's say, the lightning occurs outside, and the measurement is that I get a signal in my antenna. Okay. So I stress this drawing. It's usually it's a good idea to start answering questions in probability, especially if you have two-stage event, not a simple event, but two events, and they can be dependent or independent of each other. First thing, draw the event diagram. This is like the forces diagram in mechanics. You start solving the question by looking at your point mass and drawing all the forces that acts on it. This is the equivalent in probability. Draw the Venn diagram for the experiment. Okay. They draw it like this, but I prefer the square because this also looks like a histogram. Okay, definition of probability. So probability function. Yeah. So probability is a function, and said it's a function from the sample space to the real space between 0 and 1. The probability of omega, so probability of any result in the sample space is 1, right? When I toss a coin, it has to fall in some side. So the probability of this or that, head or tail, the sum probability is 1. Okay, that's what we even plan.
Assuming you know all you have space correctly.
Yeah.
Talk about the black swan, you don't know that this
Yes.
is an option.
Yes. Assuming, of course, that omega is complete. It describes all the possible outcomes of the experiment. Yeah. This is number 2 is more is less trivial and more important. So the probability of A or B equals the probability of A plus the probability of B if and only if A and B are disjoint. Now, what does it mean disjoint? Disjoint events are two events from the same sample space that cannot happen simultaneously. For example, you cannot get on the dice a 1 and 2. You can have either 1 or 2. So these are disjoint events. But there are events which are not disjoint. For example, like here, you can be both. Here, these events are not disjoint because you can be both smaller than 3 and odd. These two events, these A and B, are not disjoint. Okay, so disjoint events are events for which the union, so the intersection is an empty group. The intersection is an empty group. Okay. So, for example, here, if I ask you what is in this definition of A and B, what is the probability of A or B?
So 4 of 6.
Exactly, 4 of 6, because you have 4 simple events, and so it's yeah. But it is not equal the probability of A plus the probability of B, because each one of them is 1/2, so the sum is 1. Okay. That means it's a proof that these two events are not disjoint.
Ah, where is not intersection,
Yes.
disjoint, okay.
Disjoint are events in which the intersection is an empty group.
Okay,
Or if you wish in simple words, these are events that cannot happen simultaneously.
Okay.
So this was the definition, and there are some examples. Skip all that. Okay, and finally, this is the last rule. For any two events, A and B, the probability of the union, the probability of A or B equals the sum minus the intersection. Okay. Beforehand, we said if the probability of the intersection equals 0, then the probability of the union equals the sum. Now let's look again at this example. So, as you said, the probability of the intersection is 2 out of 6. Right? Okay, it's there. It's because it has two events, two simple events, 1 or 3. So the probability for a pair dice, the probability of the intersection is 2 out of 6. So here is an example. P of A is 1/2, P of B is 1/2, P of A and B is 1/3.
ah, yes.
Yes, so 1/2 plus 1/2 minus 1/3 is 2/3, which is exactly the probability of the union.
Yes.
Okay, so that sounds quite trivial, but sometimes it's a useful rule. So this is the general rule. Beforehand, it was for the specific case in which the intersection is an empty group, then the union equals the sum of the probability of individual events. But in generally, this is the general rule. Okay, and it's easy to see here when you look at when you look at this, we'll do it with colors. When you look at the Venn diagram, right? So if the area is proportional to the probability, so you ask yourself, okay, what is the probability of the union of this gap? So it's probability of B, which is this area, plus probability of A, which is that area, minus the probability of the intersection, because when I sum this and that, I counted this area twice.
Yes.
So I have to subtract this area one time. Okay. It's quite simple when you draw it like this, but when you write it like this, it's maybe not trivial, but when you look at the Venn diagram, it becomes all very trivial. And the last thing, and then I just leave you with half an hour. Last thing is the product which I gave the example before. So you can construct. I think so. Yes. Yeah, I report. The last thing is it's just the definition of the product for events. So you can make complex events by okay, what happens? I raised it. What happens if I toss the coin twice?
Yes.
So now the event space becomes like I draw before, like head, tail, head, tail, and I can construct all kinds of events and ask all kinds of questions about the probabilities of that events. A very useful tool for a product of two experiments is called the tree diagram. And the tree diagram is to visualize or to estimate the possible outcomes. A tree diagram is a diagram where on which stage it's like a process of doing an experiment in stages. Tree diagram. So I start, let's say here, and I toss a coin. So I have two outcomes, head and tail. And then I toss a coin another time, or I toss another coin, and I have another, from each possible solution here, or possible event here, or possible outcome, I have again head or tail, head or tail. And then I come to this event space, like tail, 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 head, head, tail, head, head. So a tree diagram is a way to visualize experiment that is done in, maybe if you wish, few steps or stages, few steps or few stages. So it's sometimes it's easier to think of an experiment as if it was done in stages, even if in reality it's done simultaneously. Like I'm tossing 2 points simultaneously. It doesn't matter. For the calculation of probability, the order of events in reality does not matter. So sometimes it's easier to just to think of it and to calculate the probabilities. Say, okay, let's first look at this. Then
Because they're independent. No,
Yes.
no, independence is one.
they do not depend
Yes,
on one another. Yes, that is true.
and in this tree diagram, can they intersect? In this example, I think not, but there is samples that can.
So if there are intersections, then they are not independent.
Okay.
So it's a different story. Okay, Yossi. And you'll probably also show things here and then share your screen.
Okay, what I want to show you is I'm showing the process of analyzing, looking for a linear relationship between two variables. What is the process that really people do when they are looking for such a relation? Okay, I don't think we will have time to write it. We already wrote. So what can I do against this this funny cannot minimize Zoom when you are recording this meeting? So
אבל אתה רוצה לשתף מסך, לא?
כן.
שתף מסך.
Thank you. So let's look at the example we talked about. Here. Now, first, something else. Here's an example. This is an example. It's not a physics example, but it's nice. We already understand what the regressions are and linear regressions specifically. Some company wants to find asks itself is there a relationship between the amount of money spent on some channels and the revenue it gets or the sales that follows. Okay? So those are the we call them features or predictors. Okay, and we want to ask ourselves what a TV, radio, and newsletter are predictors, and sales is what we want to predict. So we start by visualizing, which is always a good idea, as Lev said. Visualizing, we are visual creatures. The visualization is very helpful or insightful. So let's see if the Python is clear. Okay. Import NumPy is okay. Remember why we need NumPy? Just tell me now and I will.
No.
We need NumPy because. Why do we need NumPy? Basically for NDRA, the type that knows how to manage huge chunks of data in an efficient way. Okay, NumPy has many features, but this is the main reason. Knowing how to represent, to create a data structure, multi-dimensional data structure in memory that is very efficient. This is the reason, you know what raison d'être is you know this the reason of existing, why NumPy is very important. Because of that, basically. Pandas is
And we can use SciPy, no?
you can use many, but most of them behind the scenes use NumPy because it is very basic, very good package. Now Pandas also uses NumPy, but it is concentrated on two-dimensional data. Okay, because most of our data most of the human beings' data can be represented in a two-dimensional table. We call it a tabular or a relational data structure. Tabular, you know what a tab is, yeah? Yeah. Okay, and matplotlib is for creating charts or graphs. Warnings is not that important. It just you can suppress any, because sometimes packages say, you know, we are about to be deprecated and you need another, you better take the next version, and you don't care. So you say, oh, just leave me alone. So that because warnings are not errors. Warnings is just annoying messages that you may not wish to see. Now, we use pandas. You might remember that this is called a nickname or an alias. Okay, and we ask pandas to read the CSV. Okay, you know of course what CSV is. If not, just ask me. I'll say don't be shy. We're learning. Okay, you remember how CSV looks? It looks like that. What are the topics? It looks like that. The first row is optional and describes what features we are talking about. We have TV, radio. What was the third one? Newspaper, and set. This is the header. Describes the columns. And then you have values, 33, 4, 14, 32, 100, 50, 34, 2, 25. Okay, sometimes we call these lines observations. Okay, we sometimes call them observations. And those are, as I told you, features or predictors. And this is the one we want to predict. Okay, but predictors. This is the general terms. So we read it, and then I hope you remember, when we read something using pandas, we get something that is called data frame. Data frame is basically an Excel sheet, yes, equivalent of spreadsheet, yes. And I will call it advertising, and I want to print several first lines. The default of head is 5 lines, just to examine it. Okay, if you want 10 lines, you can add it to the function, add 10, and then you get 10. If you want 20, by 20. If you want to see the last ones, instead of head, you will use, if you have a dog, head and head, dog. You know what a dog is? Head,
tail.
tail, exactly. So you can, tail also gives you 5 observations, but if you say tail 10, you get the 10 last. In general, you always explore your data set before you start analyzing. Okay, you always look at it, you try to get some impressions to see whether values are missing. Okay, maybe something is wrong. Sometimes the units are mixed up. You say, okay, this is a milliliter, and maybe you need something else. Okay, maybe it is a relative speed and not the speed itself. You always examine it before you start working with it. So that's why print is good. You can print everything, or head, or tail, or whatever. Now, Seaborn is a library that is simpler to use than Matplotlib. Almost all libraries that display charts use Matplotlib, but they abstract away the details. So you can, are we recording? Yeah. Seaborn is very simple. You know, it has many defaults. So many people like it to work with. So I'm importing it, and then I'm telling it to pair plot. Pair plot means take one of the values and match them with the other. So take advertising, which is a data frame, and on X put TV, newspaper, and radio. And what will be in the Y? The Y axis will put sales. The height is just for doesn't matter. It's a relative value. And what kind of plot I want? It's called a scatter plot. Scatter plot is points. Okay, and you always have to write show in order to make it happen, for the window to appear. Doesn't matter that if you put show, everything works all the time. There are places when you can skip it, but it's not so important. Now, not taking into consideration the scale here, okay? Because we're talking about let's say in principle. In principle, you can get some notion about linear relations. Let's say TV to sales, newspaper to sales, and radio to sales. You can get the impression that maybe TV is more linearly connected to TV to sales. Okay, so don't underestimate, as let's say, don't underestimate visualizations. Okay, because a large chunk of our brain, the occipital lobe, is huge, and you can get it is very, very, very sophisticated. And sometimes you can get ideas that you don't see in numbers, or you don't see in other representations. Okay, this is something, that's why science always chopping away stuff. Okay. Now, after getting this impression, you know, it's a process that people really do in people who work in the research departments. That's what they do. 1, 2, 3, 4. This is a real process. Now we say create a heat map. Okay. I want to take the data frame and ask what is the correlation between each of the features, and I want to set a set of colors based on blues. You can say take reds, greens, whatever. It's just for. And do I want annotations? Do I want the numbers to appear within the charts? Yes. And then I get a heat map. Heat map means you have a scale of 0 to 1. What is the correlation? This one is Spearman correlation. I hope you were in the lesson when we talked about Spearman correlation. Okay, that the level of linearity of stuff, and you can see that, funny enough, things are correlated to themselves, the full. You can see symmetry, see the symmetry? You see the symmetry, of course. And you can also see that TV and cells are really, really correlated, linearly correlated. Okay? Now, after you realize that there is a strong linear correlation between TV and cells, you want to find the function itself. You want to find to analyze it and get the model. The linear model, function is a linear model, okay, in this case. So I say, give me only the series of TV and give me the series of cells. That's X and Y. Okay? By the way, the type of X and the type of Y is series. Okay? We have in Pandas, we have data frame and series. Series is a column or a serial, whatever. Now, I'm asking it, as you remember, we like to check our model. Okay, we create a model. We ask ourselves whether it is good enough or not good enough. So we create it and then we check it. But I have only one data set, so I have to split it to build, and then the remaining data to analyze and to evaluate whether I got a good model. Okay. Do you remember what a model is, by the way? Definition?
But I missed.
Okay, a model is an abstract representation of some reality. Why is it abstract? Because it doesn't consider everything. It focuses on some.
Yes.
And we talked about it. It's recorded that almost everything in our life is a model. Because when you talk about physics, you concern yourself only with those some concepts that are physics and biology and chemistry and psychology and whatever. Everything is a model. Okay? So this is a very strong definition you should take with you. Again, model is an abstract representation of some reality. How can I represent? I can represent it mathematically. I can represent it by a drawing or by concept set, something called ontology. You can also represent reality with concepts. Okay? Whatever. Teacher, student, class, university, they are all concepts. You can create a model, describe the reality of university this way. Okay, so here we import. sklearn is also a very nice package that helps us analyze data. We import a function called train test split, meaning splits the data set to 2. You see, but it's not just 2. We have X for training and X for testing, Y for training and Y for testing. Okay, we split the data to 2, test, train, and here we have X and Y. X for testing, Y for testing, X for training, and Y for training. We have 4 data sets. Basically, we have four data frames.
This is not train, this is training.
No, it's just splitting the data. Give me X and Y to train. Afterwards, give me X and Y to test whether it is a good fit. Now, X and Y, train size, it will be 70%. This one will be 70% of all the test size. This is This is not how do you call it? It's implied, so you can skip it in reality.
Because what? One minus.
Exactly. It is implied. You can skip it. Random state, because we want them to be randomly, we don't want it to cut just, you know, arbitrarily we tell it to roll it, okay, to randomize it and then take. Okay. Randomness is the essence of sampling. Okay. If something is not random, you spoil the sampling process. So why 100? Why 100? You can select any number you want, doesn't matter. Now, just for printing to shape, okay, we expect to have, let's say we have 100 lines, we expect 70 on for training, and 70 and 30 on for testing. Why? We have 4 columns, and we took 70% for testing for training and 30% for training. I can explain. I'm explaining it again. It's not clear.
No, it's clear.
Okay. Now we add. That's a technical process. We add to the training. We add another column. It is a place where it will remember the intercept. It's a technical. I remind you that an intercept is this value, y equals ax plus b. This is b, okay, and a is dy to dx. This is the exactly, slope, exactly. So we added because it needs a place to remember the intercept, we added a colon, and then we do something called OLS. OLS is ordinary least square. It's one of the ways to regress, linearly regress stuff. I give it x and y, and I ask it to fit. And LR now remembers the parameters. What is after processing? LR remembers what are the parameters, what is the intercept, and what is slope. And we can also ask it to summarize everything, and then you get a nice chart with many parameters that can examine how good the model is, and you see some of the things you will learn. And I think this semester BIC is not teach, but degrees of freedom and whatever. Okay, see, the p-value is very important. Okay, we talked about it, but it will be even clearer. Those are skewness and kurtosis and mean. These are the descriptors of the shape of the probability, and that's that. Okay, that's we talked about it. I think I did that with your friends. Okay, I also showed them how to, just for fun, how to open. I want it to be open. Why is it opening? How to create a polynomial regression is very in Python. It is very simple. As you can see, let me just remove this one. See, okay. here's a data set. You can see here. Yeah. This is a very, very nice introduction to fitting the polynomial, the several numbers. Okay, you see here, when you plot the data, they simulated a polynomial, by taking an x, and this, you see it's a polynomial of degree 2. You see that? So they got this shape, which is nice. Then they try to fit exactly as we learned. This, by the way, this is another package, but it doesn't matter. A linear regression object, it fits, and then it predicts what should be the x, the y from x test. And when they display it, you see something is missing, something is wrong. So they say, let's try another thing. Okay. So here you see that the regressor is Poly. It's named Poly. Okay, and you see that it creates when it creates it predicts the x. Okay, and then you put it together, you see it becomes more visually, it looks much adequate. Okay, and this is the code. Here they talk about if you want to create even, some people say let's create even a better fit. But this type of mistake is called overfitting. Why? Because we fit here for each of the almost, you can reach a position where you fit for each point exactly the value that you got. So the line will be very, very squiggly, but it will be perfect. What's the problem? It's not generalizing well. Meaning, it is very good on the data set, the current data set, but not as a general rule. So we sometimes prefer something that is less, let's call it accurate, but it is more general. The problem is called avoiding overthinking. Okay.
This is also depends on degrees of freedom. Yes.
Yes, but of course, but it depends. There is something that it's a rule of nature. When you become too fitted to one set of data, you pay for it, because you're not generalized enough. You can't deal with other stuff. I gave an example of a doctor that some people, a person that works in Africa, and he's very he's a specialist in some diseases. And when you take him to, let's say, to the United Kingdom, if he tries to continue exactly, it does not generalize its knowledge. It's very fitted for each case. He knows that if he didn't abstract things, he will say his knowledge is not good enough. because it is fitted for a specific set of data. Okay, this is a rule of nature, by the way. People who are data scientists learn that you must, in order to learn, you must generalize, but not be 100% fitted to one kind of data set. Okay, this is one of the major postulates that data scientists need. Any questions, Alex? Okay, basically, I think we squeezed the הפסקות, so we probably finished. Unless you want us to write now in Python, you want us to write in Python?
This is just,
Yes, you can copy paste it. You can copy. This is not part of the course, by the way. The what is part of the course is the how to create the procedure of creating analyzing data in order to find linear correlations among some features. This is also in your final project. This is so we don't have any questions.
No.
So you know what the Erev Shaket is? Have a quiet evening. You and all Israel. So let's finish.
Okay.